Hi everyone, welcome back to PRAKASAM tutorials. In this video, I am going to discuss about transformation of random variables. Let capital N random variables x1 where small n is equal to 1, 2, 3 and so on capital N to be continuous case or to be continuous random variables or to be discrete random variables or mixed random variable. Mixed random variable means both continuous or discrete. So now define another set of random variables. So xn is the x suffix n is the one set of the random variable. So next consider another set of the random variables yn where n is equal to 1, 2, 3 and so on capital N. So this another set of the random variables by the transformation of the first set of random variables x1. So mathematically and it is given by yn is equal tn of x1, x2, x3 and so on xn for n is equal to 1, 2, 3 and so on capital N. Now here where transformation t suffix n can be linear, non-linear, continuous and segmented etc. So t suffix n is the transformation. The transformation can be linear transformation or non-linear transformation or continuous transformation or segmented transformation. Assume that the random variables yn are produced by single valued continuous functions t suffix n. T suffix n is the transformation having continuous partial derivatives. There exists a set of inverse continuous functions tm power minus 1 such that xm is equal to tm power minus m of y1, y2, y3 and so on yn where m is equal 1, 2, 3 and so on capital N. That is, in a given sample space, the transformation has a one-to-one correspondence between the set of random variables x and y. In the given sample space, consider any sample space. In that sample space, xn and yn has the one-to-one correspondence between the random variables x and y. If R suffix x and R suffix y are the closed regions of capital X and capital Y, then the joint probability density function of random variables x and y can be related as integral Rx is the region, and so on integral joint probability density function of the capital N random variables, that is fx1, x2, x3 and so on xn of x1, x2, x3 and so on xn dx1, dx2 and so on dxn is equal to, so one set of the random variables is equal to another set of condition, that is integral ry is the region of the random variable y and so on integral joint probability density function of the another set of the random variable yn, that is f y1 y2 and so on yn of y1 comma y2 comma y3 and so on yn is into dy1 dy2 and so on dyn. So this is the joint probability density function of the random variable x and y. Now here Rx and Ry are the closed regions of the random variables x and y. So by applying the transformations on the random variables x and the above equation, we get region Rx and so on joint probability density function of the random variable x is equal region Ry, and applying the transformation here y x1 x2 of x1 y y suffix x1 x2 and so on xn of x1 is equal to t2 power minus 1 x2 is equal to t2 power minus 1 and so on xn is equal to tn power minus n into determinant of j dy1 dy2 and so on dy1. In the second term, applying the transformation, we get this expression where determinant of j is the magnitude of the Jacobian of the transformation. So the Jacobian is the determinant of the matrix, determinant of a matrix of the derivatives, and it is defined by j is equal determinant of dou t1 power minus 1 by dou y1, dou t power minus 1 by dou y2 and so on dou t1 power minus 1 by dou y1, dou t2 power minus 1 by dou y1, dou t2 power minus 1 by dou y2, and so on, dou t power minus 1 by dou y1, and so on, dou tn power minus 1 by dou y1, dou tn power minus 1 by dou y2, and so on, dou tn power minus 1 by dou y1. So this is the Jacobian determinant matrix. The joint function of the random variable y is similarly, okay, in previous, the joint density function of the random variable x in terms of the random variable y. Similarly, in the reverse case, the joint density function of the random variable y is region Ry, and so on. Giant integral giant probability density function of the random variable y is equal transformation f of x1 f x1 x2 and so on xn of x1 is equal to t2 power minus 1, x2 is equal to t2 power minus 1, and so on, xn is equal to tn power minus 1, Jacobian matrix into dy1 dy2 and so on dyn. So by removing the integration on both sides of this equation, we get the giant probability density function into giant probability density function of the random variable y into dy1, dy2, and so on dyn is equal giant probability density function of the random variable x1, giant probability density function of the random variable x transformations into Jacobian matrix. So this is the concept of transformation of the random variables. So some important conditions are for a single random variable transformation between x1 and x2, that is capital N is equal to 1. So capital N is equal to 1, y is equal to transformation of x, or x is equal to inverse transformation of y, and fy of y is equal to fx of x is equal to t power minus 1 into determinant of dt power minus 1 by dy for single random variable case. Now here we can explain n random variables, transformation of the random variables. And what is that condition? This is the mapping condition, and this is the xm inverse matrix t power tm power minus m, y is equal to transformation of x, x is equal to t inverse of y, n random variables. Jacobian matrix for n random variables. Okay, for single random variable condition. And the second point is for two random variable transformation between x1 and x2 and y1 and y2, that is n is equal to 2, the giant density function is f of y1 comma y2 is equal to f of x1 comma x2 into two random variables Jacobian matrix, that is dou x1 by dou y1, dou x1 by dou y2, dou x2 by dou y1, dou x2 by dou y2. Okay, so for single random variable condition, for two random variable condition, linear transformation of the random variables.